All right, you guys, we are about to start Chapter 2, Electricity, Section 2, Electric Current. We are getting into the good stuff. So follow along, pay careful attention, and take notes. All right, the first topic we're going to talk about is the flow of electric charges. Remember, charges are either a negatively or positively charged atom. So they can flow, and we're going to talk about how they can. All right, so first off, an electric current, the continuous flow of electric charges through a material. Now, last section we talked about static electricity. Static electricity is not an example because they do not flow continuously. Remember, static is a buildup of charges. So they do not flow continuously. Just when they hit another object that has the opposite charge, they will equalize, and that's how you'll get that shock. So it's not considered a current because it does not flow continuously. Now, the amount of charge that passes through a wire in a unit of time is called the rate of electric current. All right, so that's the rate. And the unit for the rate of current or the continuous flow is an amp. An amp is what is the unit of current that passes through at a given time. The number of amps describes the amount of charge flowing past a given point each second. All right, so it describes how much current per unit of time is passing by. So that's an amp. All right, so current in a circuit. Electric current does not automatically exist in a material. Current requires a specific path to follow. To produce electric current, charges must flow continuously from one place to another. So charges have to be able to flow. So again, it's not like static electricity where they kind of build up on objects. It's got to be able to flow. All right, it requires an electric circuit. An electric circuit is a complete, unbroken path through which electric charges can flow. Now, we're going to talk about conductors and insulators because there's different things, different types of materials can allow charges to flow more easily than others. Charges can flow easily through a circuit made of metal wires. So as you're probably most familiar with, charges do flow through metal. And that's why a lot of our power lines, as you can see, we want charges to be able to flow to give us a current. So we usually use metal wires. And here's why. Charges do not flow easily through every material such as plastic or rubber. So you might be familiar with these things. So they do not flow through plastic or rubber very easily. A conductor, such as our above metal wires, transfers electric current well. So conductors conduct electric charges or allow them to pass through them. An insulator does not transfer electric charge well. So we would not make power lines made out of plastic because the current is not going to flow very quickly or very well. Now, let's talk about conductors a little bit more in depth. Aluminum, copper, silver, iron, and other metals are good conductors. You can look at the periodic table and it's broken into metals and nonmetals, and the ones that are labeled as metals are good conductors. All right, they are materials in which charge can flow easily. All right, here's why. Their electrons are bound loosely to their atoms. Now remember back from the first section, the diagram of an atom, protons and neutrons in the center, electrons circling around. So for metals, their electrons circle around the atom, but they're pretty loose around them. They can kind of separate from the atom pretty easily. So that metals don't hold on to their electrons very tightly. So we say these loose electrons are called conduction electrons, and they're able to move throughout the conductor and form an electric current. They carry an electric charge. So remember, because conductors electrons will move easily, their particles often become a positively charged atoms, and the current can move pretty quickly through them because their negative charged electrons can move through these materials. Insulators, on the other hand, such as rubber, glass, sand, plastic, and wood, are examples of good insulators. They are materials in which charges cannot flow easily. Now, they are used to stop the flow of charges, as you can see in the diagram to the right, and I'll explain that a little bit more here in a second. All right, the rubber coating on an appliance cord keeps the flow of charges through the metal wires from transferring to you. So if you were to touch the metal wire as charges were going through it, the charges would flow to you, and that would be pretty ouchy, pretty dangerous. So that plastic covering around the wires keeps, the charges cannot flow very easily, if at all, through plastic. So that keeps the charges from flowing to your hand. So it's a good insulator. Now, voltage. Voltage is another key vocabulary term for this section, and it gets a little tricky, so buckle down and listen closely. All right, in order to best understand this concept, let's think about a roller coaster. I've been using these examples of roller coasters a lot, especially in our energy forms unit. All right, the higher the chain in which the roller coaster cars are attached carry the cars, the more potential energy they gain. So just think about yourself on a roller coaster. Now you get on, you're all excited, and the car carries you up the hill. All right, the higher you go up the hill, the more potential energy you gain. Now remember, the car itself is not moving itself. There's a motor that's carrying the car to the top. So the higher up that car is placed, the more potential energy it's going to store up. Now, after reaching the hilltop where you have high potential energy, and then rush to the bottom of the hill where you have low potential energy. So you're going from an area way up at the highest hill, an area of high potential energy, and rushing to the bottom where you have low potential energy. Now, just like the roller coaster creates a difference in potential energy because you went from a high potential energy at the top to a low potential energy at the bottom, so does an electric current. Now, the difference in electrical potential energy between two places in a circuit is called voltage. So let me repeat that so you got that. It's the difference in electrical potential energy between two places in a circuit, and that's called voltage. Voltage causes a current in an electric circuit. So it's the amount of force pushing on an electric current is what voltage is. So it causes a current, and essentially what it is just a difference in two places in the circuit. So it's a difference in the electrical potential energy. Just like you on the roller coaster, you went from a high potential energy to a low potential energy at the bottom of the hill. Voltage is the difference in electrical potential energy. All right, so voltage sources. just like the roller coaster car depends on the motor of the roller coaster to pull the chain to drag the car up the hill to where you'll have that high potential energy, an electric current also requires a source of energy. So on a roller coaster, you have a motor that's actually bringing you up to the top of the hill so that you can get that high potential energy. So we need a motor, or we need a source of energy in an electric current so we can get a great difference between our electric current. A voltage source is a device that creates a potential difference in an electric current. Examples are batteries and generators. So they are voltage sources. They create a potential difference. Now you can see some pictures of batteries and then in a generator. Now, they have two terminals, so you guys know there's a plus and a minus on a battery. They have two terminals, and the voltage between the terminals causes charges to move around the circuit. So it creates a difference, a potential electrical difference, just like the roller coaster. So it has two terminals, and the voltage between the terminals, or the difference between the terminals, causes charges to move through the circuit. So there's a difference between their charges, and that difference causes them to move through the circuit. Now, resistance is a big factor. We've got to get these key vocabulary terms down. All right, resistance, another electricity term, is a measure of how difficult it is for charges to flow in a material. The greater the resistance, the less current there is for a given voltage. It's like a roller coaster having rusty wheels, supplying resistance. So it's a measure of how difficult it is for charges to flow in a material. The unit of measure of resistance is called an ohm. And you can see that little symbol there, that is the symbol for an ohm. It's a unit of measure of resistance. Now remember, resistance is a measure of how difficult it is for charges to flow. Slide here, we're going to talk about some factors that will determine resistance. Now, there are 4 factors that will determine resistance in a wire. The first one is the type of material. Now, insulators have a high resistance. Conductors have a low resistance. So remember, insulators such as glass and wood and plastic, they're going to have a high resistance. They're going to hold back the flow of charges. It's going to be harder for charges to flow through an insulator. Conductors, like your wire, your metals, they have a low resistance, really easily flowing. All right, also the length of a wire. A long wire is going to have more resistance than a short wire. Now you can kind of look at the diagrams here. Try to show you. The diagram of the long wire, of course, is going to provide more resistance here than the short wire. So it's harder to flow through a longer wire than it is a shorter wire. And you can read here, a short pipe has less resistance than a long pipe. Similarly, a short wire has less resistance than a long wire. So kind of just look at this diagram here. There's more resistance, or it's harder for electricity to flow through a longer wire, just like the tunnel here, or the pipe. All right, diameter, or the width of the wire. Thin wires have more resistance than thick wires, and you can again look at the diagram in the left-hand corner. You can see that you have a wide pipe compared to a narrow pipe. So the narrow pipe, of course, has more resistance than the wider pipe. So a wide pipe has less resistance than a narrow pipe. Similarly, a thick wire has less resistance than a thin wire. All right. And the fourth factor that determines resistance is the temperature of the wire. Resistance increases or goes up, more resistance as the temperature of a wire increases or goes up. So the hotter the wire is, the more resistance or the harder it'll be for charges to flow. All right, and the last topic I'm going to talk to you about is the path of least resistance. All right, so charges, they like to take the easy way out. They like to take the easiest route they can. So if they have two paths to take, the current will flow through the path in which the charges can flow the easiest. So I want you to check out the diagram below of the bird sitting on this metal wire. So all these birds are just chilling out on this metal wire here. All right, so it's like the bird sitting on an uninsulated wire, no insulation, so it's just the metal wire. The charge can either go to the bird's body or continue through a metal wire. Which path offers a path of least resistance? Would the electric current just continue to flow through its wire, or would it choose to take the path of going to the bird's body, and where there's feathers and body tissue? Which one's going to offer the lesser amount of resistance? So you guys think about it. What do you think? All right, you're thinking right. Absolutely, they're going to continue going through the wire just as they had before. A wire is a conductor. The bird's body is an insulator. It's going to be harder for the electricity or the electric current to flow through a bird's body than it would be to just simply continue on its path through a metal wire. So just keep all these terms in mind. Please practice your vocabulary so these terms will all make sense. You are welcome to go back through the PowerPoint and re-listen. Okay, so complete these questions on a separate sheet of paper. Number 1, what happens when an electric current is produced? Number 2, explain why electric current cannot exist if an electric circuit is broken. Number 3, what types of materials are good conductors? Number 4, give 2 examples of good insulators. Number 5, how does voltage cause charges to flow in a circuit? And number 6, what is resistance? And give 4 factors that determine resistance. Now, once you've completed the questions on a separate sheet of paper, be sure that your notes are complete, these questions are answered, and you can now make your vocabulary flashcards. Once all 3 of those things are complete, you may take the test. All right, good luck.